So this is a talk about metaphors in Python programming, focusing on some advanced Python structures. I'm James Powell. We're at PyData Berlin. It's Friday, June 30th, 2017. I don't know that we have enough time to get into any introductions, but if you want to follow me on Twitter, I'm Don't Use This Code on Twitter. If you want to email me, I'm james@don'tusethiscode.com. I've been doing enough corporate training recently that I probably should change my email address because that might be sending the wrong message. I'll actually try and show you in this tutorial some things you really should actually do when the circumstance suits you. Structure-wise, what I'm going to do is I'm going to be sitting here in the front, so you don't have to see my goofy face. You can just watch the screen up there. And I'm going to try and lead you down a very specific path to get an understanding of 4 pretty advanced parts of the Python language as quickly as we can. As I said before, this was originally a 3.5-hour tutorial at PyData Amsterdam, and we're going to try and compress that into slightly over 90 minutes. I have the three of the 4 topics that we'll cover form a really nice story to push this idea that there are some core metaphors, some ways to really think about and to fundamentally understand what these features are about that lead you to a greater understanding of how they can be used in Python and give you a strong enough mental model that you can start making reasonable predictions about what happens when you mix and match them, or what you might be able to do in terms of modeling complex programs using these features. But in order to really drill home the idea that there are some metaphors in Python, because a lot of people, I said this before, but a lot of people, they get really far with just data frames and ND arrays and simple functions. And what they don't necessarily realize is that when you're dealing with simple functions, there are some core metaphors there. Even the idea of modules and functions, something that's relatively new in terms of computer science. If you go looking, you'll find a talk by, I believe it was Leslie Lamport, about how in the early 70s, people didn't really know what modularization meant. It was a topic that people were beginning to think about, but the very clear idea we have in our heads of what it means for a function to be a function, or what it means for a module to be a module, is something that had to be discovered. It's something that all of us benefited from in our education, because we could just take it for granted, just assume that it meant exactly what, and just be able to intuit what it means. But it's something that somebody actually had to sit down and think about. And I want to show you that there are other parts of Python that have that. So I'm going to start with one of the most controversial, one of the most ridiculously controversial features in Python. I don't know that I'd call it a feature, but it's an interesting way that Python does things. The feature I'll start with is called metaclasses. And I'm sure you've all heard of metaclasses. And I'm sure all of you have heard somebody say, don't use them, they don't make any sense, they're magical, they're scary, they're pointless, there's always a better way to do it. And that was more or less the genesis of this talk. Genesis of this talk was people looking at that feature, not really fundamentally understanding what the feature was, and then saying, well, I don't see how it's useful. I'll tell you, metaclasses aren't useful for anything and everything. Clearly, if you have a fish and you need to debone it, don't use a metaclass. Use a paring knife, I think. I'm not sure. But use some sort of knife. Don't use a metaclass. There is one very common problem that has many different manifestations, where a metaclass is one of only about 2 common ways to solve that problem. And let's talk about those 2 common ways. In order to do that, I'm going to give you a very simple challenge. So let me open up a Vim, and I'll put a split. I'm going to have 2 pieces of code here. And I want you to imagine something in your mind. I want you to imagine a very common circumstance in your mind. There is some, let's actually do this with a different one. Let's write this as library.py, and we'll do a vsplit with user.py. So we have 2 files here, library.py and user.py. And imagine the very common circumstance where there's some library code that you can't change and some user code that you can change because you're the user. This happens all the time. You know, we're working with open source projects, but it's not guaranteed that if there's a bug in the library, we can just go change that code without necessarily upstreaming it, because this code may be deployed via some mechanism like pip, and our own personal changes won't be pulled down. So in many cases, we have to work around problems in the library until somebody can put in a bug request or a pull request and fix it upstream. In other cases, Maybe there's an organizational reason where some code is written by somebody else, they control that code, and we can't change it. It turns out it's common enough that there's some code that we can change, and there's code that we can't change. So for the purpose of this one little mental exercise I'm going to present you, let's imagine that you're the user. The only code that you can change is on the right-hand side of the screen, user.py. You cannot change the code on the left-hand side of the screen. Let's say that in library.py, somebody created a class, and they called that class foo. And in that class, they had some method bar. And it doesn't really do anything interesting, okay? Doesn't do anything interesting at all. Let's say in user.py, you want to make use of the code that they had, because this wouldn't be a very interesting exercise unless you made use of their code. So you say from library, import foo, and you want to subclass it. You want to create your own class. So we'll call it cux, and we'll subclass from foo, and we'll write our own method here, baz. And what baz is going to do is it's just going to return baz plus self.bar. Okay? This may be so simple that you don't even see how common it is. And you might have a little bit of difficulty picking out the pieces that are important. The two pieces that are important are as follows. One, we're using somebody else's code by subclassing from it. And two, we're calling a function that we didn't define that was defined on the left-hand side. Here's the challenge. How can I, in some Python code, make sure that if I'm running user.py, I get an error the moment I try to define my class, and we'll call our class something a little bit easier. We'll call it we'll call it derived, because it'll make the example a little bit easier. And I hate saying foo and bar all the time. There we go. How do we make sure that base has a bar method? That's the only thing I'm asking you. This is actually a very easy thing to do. But let's take just a minute. You have a little bit of code at your terminal. I've only written 7 lines of code on the screen. How do you make sure self.bar exists? Because you don't control library.py. Because you don't control library.py, whoever wrote that could accidentally remove the bar method. They could delete it, and your code would break. So how do you in your code make sure that their code didn't screw up? How do you do it? Take a minute and think about that. Try writing some code, maybe. I'll give you about a minute or two. There's many ways to do this. In fact, for both sides of the question I'm going to ask, there are many ways to do this. Does anyone not see why it might be important to determine this constraint? Obviously, I'm the library author. You're the user code author. If I change this to bar, I just ruined your day. All your code breaks, right? So you got to make sure that I'm on the straight and narrow. You need to keep me honest. And you can't change my code. You can't say, can't add lines to library.py. You can only add lines of code on the right-hand side of the screen to user.py. So does anybody have an idea what we could do? A lot of choices. In the back, what we might do? Just as simply as possible, what do you think we could do? We could check it in our constructor, so we could say def init self if not has attribute self bar raise type error, something like that. We could do it even simpler, right? Couldn't we just do this? If base doesn't have a bar attribute, now, this is not perfect because bar might come into existence through many different means. But if base doesn't have a bar attribute, this code breaks and it breaks immediately. This assert will fail, and you'll never run the derive code. It'll just break, right? And it'll break on your end, so at worst, you'll get that error immediately, not when you actually call and use the derive class. Another simple way is you write a unit test, and in that unit test, you just do And this is probably how you might do it. You might have some unit test that creates a derived instance and calls d.baz. And you say, well, I just run my unit test before I deploy the code to production. If my unit test passes, it means my class is correct. My class is correct. It means all the hidden constraints that it has from all of its base classes are correct. And that's what I do. But in either case, you're able to ensure something is correct before it actually runs in some production environment, either by writing a unit test that actually calls it, or by simply putting an assert at the top of your code here. This is a very easy thing to do in Python. Let's try to understand what's happening in this example. We have two pieces of code, library.py and user.py. There is a constraint that needs to be enforced. User.py needs to make sure library.py is written in some fashion. So what you could say is that the user code is enforcing a constraint on the library code. The user code is making sure the library code is written in a particular fashion. Let's back this up a little bit. Let's do the following. So now I change the code a little bit. The library code calls the baz method. It does not define it itself. It assumes that the only time you'll ever use this base class is when you create your own class deriving from it. And it assumes that when you do this, you have to implement baz. Now, you could say that the authors here might just implement some dummy one here, like raise, not implemented error, or return something. But let's just assume that for some reason it doesn't make sense for them to give a dummy implementation, that they necessarily require that you give your implementation of baz, because the problem doesn't make sense unless you do. Let's say that the roles are switched. You're no longer the user, you're now the library author. So you only control the code that's on the left-hand side of the screen. You don't control the code that's on the right-hand side of the screen. As the library author, you're providing code to users to use. You need to make sure they don't screw it up. You need to make sure, hey, if you're going to use my class, you implement this method baz. So the first thing you might do is you might say, hey, if you do not implement baz, then I hate you. You can put a little comment, right? But that doesn't really help because nobody reads comments. They read comments they'll read documentation first before they read comments, and nobody reads documentation. So that's not really going to help much at all. Here's the puzzle that I give to you. You can only touch the code on the left-hand side of the screen. You cannot touch the code on the right-hand side of the screen. How do you, on the left-hand side of the screen, make sure that anybody who uses your class on the right-hand side of the screen necessarily implements the method baz? In other words, how, as a library author, do you enforce a constraint on user code? In other words, how do you enforce a constraint in Python from a base class to a derived class? We saw the other way around was trivial. There's like 10 different ways to do it. I gave you 2 already. How do you do it the other way around?
If you don't want to instantiate the base class itself, but only derived classes, you could check it in the constructor of the base class.
Like this, you say init self if not has attributes self baz do something. Yep. Yeah, but there's no guarantee that they'll call your init. Right? Anybody else? Use an abstract class. Hold on to that for a second, because that is an answer, but it's an answer that's further down the chain from what the answer I'm driving at is. The answer I'm driving at actually is how abstract classes are implemented. So can anybody go a little bit closer to the language features? It's a good answer. That's how you'd actually do it using part of the standard library. But can anyone go a little closer to the language features? Anyone see this is a fairly common problem? You need to give code to other people and make sure they don't screw it up. Who here has coworkers who you're like, oh boy, we better be careful if we give them this code. They're going to screw it up. Nobody? Okay, a couple people in the back. Are they here? Who has coworkers who are here, who are that way? You're like, please come to PyData. You need to know how to do it the right way. Couple people. I told you in the kind of warm-up that there are protocols in Python. It turns out that Python has a couple of dominating characteristics if you look at how it's designed. One of the dominating characteristics is protocols. One of the other dominating characteristics is that everything is dynamic. There's a very rich runtime, and because there's a very rich runtime, there's ways to hook into different steps of that runtime. What I mean by there being a very rich runtime is that if you're a C++ or a C or Java programmer, and you see a class statement, what do you think in the back of your mind? You think the compiler reads through this, does some stuff off to the side magically, and then I can use it. Python strictly evaluates code from top to bottom on a script. And every statement in both of these scripts are executable code. The class statement in a Python script is executable code. What does it do? Well, in the parsing step, the Python interpreter grabs all the stuff under the class statement, turns that into bytecode, and then creates a certain bytecode called create class that will create this class. And so what you can see, if I give you a Python terminal here, is if I say if I have a function, I'll just put this into a scope, that creates some class, I can create a class and a function. And if I look at the bytecode that's generated, we can see what actually happens. When that code is run from top to bottom, Python does a load build class, sorry, it's not create class, it's load build class using all that information, which means there's no reason in Python why I can't do this, other than it makes no sense whatsoever. I can just tell Python instantiate this class object 10 times in a row. You never do this. It makes no sense. It's pointless. But you can do it because that class statement is actually executable code. It's actually the Python interpreter going out and doing something, and the thing that it's doing is creating an object called foo that has a method called call that creates instances of that object, subject to a lot of the details of how the thing works internally. That should give you a hint. Because Python has hooks more or less anywhere in its runtime, you could think, well, hold on a second. Something is happening in executable code to create derived. There's actually some process inside the interpreter that goes in and creates that. Could I hook into that? And it turns out you can. There is a method in Python called build class. And it's part of the built-ins. And build class is just some function. Look, it has underscores before and after, and you see how it kind of matches up to the build class opcode? It's just a function that's called whenever Python builds a class. As simple as that. I don't remember all the arguments that it takes. I think it takes, we'll just do this. Okay? And we'll just see what it passes, or what it returns. We'll print that, and we'll call the original build class. And we'll just pass these on. So let's see if this, I don't know if any of the code that I wrote will actually work, but let's check and see if it does. Python user.py. And then let's do this. Oh, we have to actually have our import from library import base. And build class might have, I think build class doesn't have a underscore here. I think it's like that. I don't remember all these details. Honestly, none of these details are that important to remember. Maybe I have to stick it on the built-ins then. Okay. Think it might be like that. Line 5 here. This one. No, it's here. It's here. Oh, you know what? It is actually. I got it right the first time. Never second guess yourself. And then this is import built-ins. There's always some mechanics to this. There we go. So let me make this a little bit smaller. You can see the whole code. I overwrote this build class, and you can see it's printing something out. Every time. Every time I construct a class, We have some hook, and we can do some stuff there, right? So obviously, we could just do, notice the arguments are the class you're creating, the name of it, and the base. So those are the arguments. It's the class, the name, and the base. Or the bases, actually. So here, we could just do assert, or if not has attribute, class, baz, raise type error. Just like that. And we'll see that works there. Nope. And you'll see that this more or less should work. But anyway, you get the idea. The idea here is that, and I think this might be a. Oh, sorry. It gives you something slightly different. Build class gives you something slightly different. It doesn't matter. It honestly does not matter how this feature actually works. What really matters is when you need to use it, you look it up. This is not the right answer in terms of how we do this, but it should get you thinking. There's some protocol in Python. There's some metaphor in Python. Everything that you can do that has some runtime effect probably has some hook somewhere. The hook for building classes is called build class. You get in there and you do anything magic you want. The real answer for this, and what I wanted to lead you to, is the idea of a meta class. And I want to show you where meta classes are important. The way a meta class works is when a class is actually constructed, first build class is called. You don't usually hook into that. And then the thing that actually constructs derived classes is the meta class itself. And the meta class itself is just another class that has methods like new. And instead of creating a new instance, this creates a new class. Name, and I know the arguments for this, bases and body. New. And then here you can see, and this has to derive from type. And you can see here again, it's just printing things out to the screen. Once when I create my base class, and once when I create my derived class. And here I would just say if baz, not in body, because that's actually a dictionary, raise type error, and throw my error here. And the idea here is the meta class is one of the mechanisms you have for enforcing constraints from a base class to a derived class. And that's all it is. And almost every time you've seen a meta class in production, it's been exactly this. Somebody wrote code on the left-hand side of the screen, and they had to do something to force you on the right-hand side of the screen to not screw it up. What the meta class is it inserts itself into the process of building Python classes and allows you to do whatever you want. In this case, check that something was implemented, so that something is implemented, that something exists. In the collections.abc module, there is a meta class called ABC meta. All it does is it gives you the ability to systematically do this, to make sure that certain methods are abstract, they must be defined, to systematically do all of what I showed you there without having to write all the code yourself. But if you think about it, where are meta classes used? Meta classes are used in ORM, object models. Why? Because they need to make sure that the class that you're constructing, the derived class for that ORM object, satisfies certain constraints. For example, that its fields have certain layout to them. If you think about it, a lot of problems that you'll run into fit this model very easily. One of the areas where it really dawned on me what a meta class was is that we had, in a production environment, a bunch of tests running. And all of the tests derived from a single common test base class. And the reason that was the case is that our single common test base class, we connected to a test database, so all our tests would use test data. Makes sense, right? It's in a big bank. One of the problems was we needed to make sure that that connection was made every time you ran a test. Because accidentally, some people were running their tests and they forgot to derive from the right place, or they derived from the right place, but they forgot to call a special method, the setup method in your unit test class. They forgot to call a setup method to make the database connection, and their tests were failing because they were either connecting to a default database, which didn't have any test data in it, or they weren't connecting to a database at all. The problem, as it occurred to me, looked like this. We have a bunch of classes in production that people have written. We have one base class that maybe one or two people have control over. How do we make sure all these other pieces of code satisfy some constraint determined in that base class? There were two solutions proposed to it. Solution one, write a meta class. Just make sure if you derive from this test class, you satisfy certain constraints. You do certain things in a certain fashion. We know exactly what you're trying to create. We know the class you're trying to create. We know its layout. We know what's implemented there. We can add any arbitrary lines of Python we want to do that. Solution two was write a script that greps through everybody's code to look for problems and then send them an email. I'll let you guess which solution won. It wasn't the meta class. So in the end, we actually ended up just grepping through everybody's code to look for errors, and there was a script that ran in the background, and it was just an entire mess because everybody would get emails every day saying, your code is out of variance, and then they'd send an email back saying, I don't know what you're talking about, and someone would say, no, we need to get your boss involved, you didn't write the code the right way. Instead of writing a 20-line meta class that just says, look, you're trying to create a derived class from this base class. If you don't do this, this, and this, your code won't even execute. It won't execute without an error. And that's all the meta class is, and that's where it's applicable. Now, this is not tied into the full story I want to show you. The full story I want to show you are for a lot of features of Python that are much easier than meta classes, much easier to understand. But the core here is to see that what you have is a very, you have a piece of Python that looks, by all appearances, to be very complicated and completely inscrutable. But when you get to the core of what that metaphor is, namely, we have base classes and derived classes. Sometimes one needs to make sure the other one's written in a certain way. Sometimes the other one needs to make sure the first one's written in a certain way. You can see you have essentially one or two common ways to make sure that a base class, from a base class, that a certain derived class satisfies certain constraints. There's actually a brand new way to do that in Python 3.6. I'll let you look it up on your spare time. It's called init subclass. It's a new method that just hooks into when you create subclasses. And the reason it was added is that meta classes have some implementation details that are a little bit complicated. But as I told you at the very beginning, the implementation details simply do not matter. For most of you, these are features that you will need to reach for when you see a problem that matches this. Until you need to reach for this feature, you don't have to really put a lot of thought to it. The only thing you should remember is, where is this feature? What's the pattern for this feature? What's the metaphor that this feature implies? And if you know that, then when you look at the details, you'll see, well, actually, the implementation is not perfect. There's some weird corner cases, and that'll lead you towards something like init subclass, which gives you maybe a cleaner implementation. But until you get to that point, really the only thing that I would care that anybody would remember is the core metaphor itself. Because you can see, I don't even remember, I do this stuff all the time. I don't even remember the arguments. I don't even remember the syntax. I don't even remember what the types that are passed back and forth are. I kind of have to guess, I have to play around. But I know fundamentally what does this feature mean, and I know when to reach for it, and I know when it's appropriate and when it's not appropriate. With that said, let's take a look at some easier features, and you'll see that same pattern of there's a core way to think about this, and if you have that way of thinking about this feature right, then the rest is just details. Details you don't have to worry about until this is something that you need to reach for and use. And we will, by the end of the 90 minutes that we have allotted, figure out what a paring knife is. So we'll be able to stretch that analogy a little bit further. Let me show you a much easier part of Python. It's a feature called decorators. I'm sure you've all used decorators before, and you've probably seen them before. I want to show you what they mean, what they fundamentally mean. And they tie into another important characteristic of Python, the language. Oftentimes, when people look at this feature, the watermark for whether a talk about decorators is an easy talk or a novice talk or an intermediate talk is whether they talk about higher order decorators. And the bar for if you're in an interview, if you're an advanced candidate or a junior candidate, is, well, you can write a simple decorator. Can you write a decorator that's 3 levels deep? And what I want to tell you is all of those are really just simple details that follow from first principles if you understand what a decorator fundamentally is. Here I have a file called dec.py. I want to show you something. I told you that in Python, everything is executable code. The Python execution model is incredibly simple. In fact, it's so simple that you might even say that one of the reasons that Python code is very difficult to optimize in practice is because its execution model is so simple and so dumb, just executing lines from top to bottom of a script, and that's it. So you saw with the class, there's some execution, right? There's a build class bytecode. That build class bytecode actually does this work of making that class available for you to use. Same thing happens with functions. If I have a function called, let's call it add, that adds two things together, there's a bytecode for this. And the bytecode for this is called build function, I think. Let's find out. Let's find out what the bytecode is. Sorry, it's called make function. See, I can't remember any of this off the top of my head. I have to grep. I do this stuff. I'm in the Python interpreter all day long, looking at bytecodes all day long. I can't even remember this stuff off the top of my head. So if you look at this and you're like, there's no way I'll remember this more than 2 minutes after you finish talking. And by the way, I'm already kind of asleep already. Don't worry. I was told, by the way, the first time I ever gave a talk in Berlin, this is a aside, but the first time I ever gave a talk in Berlin, I tried to include some jokes, and somebody came up to me after the presentation and said, you know, the German audience, they don't really care for jokes, they just want to see code. So just let me know if I can stop the joking, if the joking is really getting in your way of appreciating the pure code. I just want to make sure I have the audience right. Does anyone here not like jokes? One person. And you don't like any form of humor whatsoever. Just show me the code. I'm wasting your time here. Okay. I have a function called add, right? There's some bytecode for making a function. We can't really intercept that bytecode for making a function. That's not possible. As I said, Python's got a lot of hooks in a lot of places, but they're not everywhere. They're usually driven by specific need. If you said we need a hook to hook into the creation of functions, somebody might ask you, well, why? And it would be kind of hard to come up with a really good use case for that, for some reasons we'll see very shortly. But that said, what I told you was, this thing here creates some actual, this is some actual executable function that creates an actual object. Let's see that in practice. What I'll do is I'll run my script here with the -i flag, and the -i flag will drop me into an interactive console with the result of the script. So I'll show you what that means. We'll say z equals 10. If I do this, I can actually interact with the results of the script after it's run, so I can see all the things that were created. This is similar to, if any of you have ever used idle, this is kind of similar to what happens in idle. What you can see is this add bytecode, this add thing is actually an object. It's a very rich object. In fact, a lot of important information for this object, just like any other object, can be queried directly from this live. So, sorry, add is just some function. You can even see it sits at this memory address, in case that's at all useful. You know, if you look at this, this is the code for it. These are all the bytecode behind it. You know, you can see that it has a default argument. Hey, look, that's the default argument. It has a little doc string. You can see it there. I bet you it has a name. Oh, that's the name of the thing, right? If I say sub equals add, you can see it's just a very, sorry, if I do sub equals add, you can see the name is something that is inherent to the object when it was first created. It's part of the protocol for creating these functions, and binding it to a new variable name doesn't change anything about that underlying function. So there's a real function here, right? Now, we know from writing simple functions that when we have a function, we can pass anything as an argument, right? So I could write a function called log, and maybe it has one argument called f. I wonder what that's going to be. And it has two arguments, x and y. And I just print out f.name, x and y, and I just return f of x and y. Remember, this syntax, all it means is f is some object that implements some method, call, go find that method, implement it, execute it, and pass it the arguments x and y. So when I run this code here, you can see add is just something that has call implemented. The call on it just evaluates the code inside the body of the function. So if I do log of add 10 and 20, you can see it logs the call to this add function. Very simple. All it does is it prints out the name of the function, the arguments that were passed, and then actually executes it for us. You can see Z is the result. Very simple. And I'm just passing to this function log another function, x. Now, you might say, well, if I actually wanted to do this as some logging mechanism, this is a real pain in the butt. Because I'd originally had some code that looked like this. 1 plus 2 equals... I originally had a bunch of lines of code that looked like this, and I actually want to add in a little bit of logging information to this code so that I can, when I run this script, it actually tells me some other information like how many times this add function was called. You know, maybe this function is a little bit more complicated than adding two numbers. Maybe it makes a database connection. Just want to log it. And if I actually wanted to use this little thing I wrote here to log this, I might even do this. The return value is that. And I'll even log the return value. If I wanted to actually use this, oh, it would be a real pain in the butt, right? I'd have to change this user code. And this is something that we rarely want to do. Here's another core lesson about Python. Python is somewhat rare in terms of the programming languages you might use that has as clear this idea of escalation pathways, or whatever you want to call it. The idea being this. In Python, you're encouraged to write the dumbest, simplest code possible that solves a problem in front of you. The reason for this is if you ever talk to the core developers, the Python core developers, and I've talked to many of them, they're all very nice people, and they want you to spend as much time with your family as possible. They don't want you to be at work until 11 p.m. trying to figure out how can I make this code robust for a problem that nobody's even asked me to solve. How do I predict what's going to happen 10 months down the line, because I know that I have to rewrite all my code if something small changes about my architecture. Instead, the Python programmer said, we want to have a world where people are well-adjusted, where kids grow up with their families. And so what we'll do is I'm sorry for the joke. Sorry about that. What we'll do is we'll write a language where it's okay to do the simplest, stupidest thing possible as long as it solves a problem. And then we'll make it easy to take that simple, stupid code and make it slightly more complex when the need arises. You see this as a common pattern throughout Python. There's often a very simple way to do something, then a slightly more complicated way to do that. And what happens is the end user code doesn't need to get written. You try to minimize how much code you have to rewrite to slot in that more advanced behavior. I can show you some examples of that, but I think we'll run out of time. So if you're interested in that, I can show you a lot of examples of those. And they fit together very nicely in some steppings. I can tell you about 3 or 4 different steps where you say, this is the dumbest way to write it. Then when you realize you need this, you make this small change. Then when you realize you need something else, you make this small change. And the most complicated version of that code requires you to rewrite as little as possible and makes it okay for you to write the dumbest version to start with. One thing I love about Python, which is the actual code you might see in production to solve a problem, looks very similar to the stupid code that you saw in some book or some tutorial online, and that if your problem is a little bit harder, usually there's a slight extension to that to implement it. I never saw this in C++. I programmed in C++ for many years, and the code you'd see in a book looked nothing like the code anybody actually wrote in production. Yeah, amen. So here, the problem is we want to add a little bit of logging to this add function, and it kind of sucks to have to rewrite this. So what we could say to ourselves is, you know what? I know Python is a dynamic language. I know that this def statement is something that can be executed. Well, when I have it in a module, it gets executed from top to bottom. Well, couldn't I create a function inside another function? I mean, a function just executes code, right? So I could just create another function in here. So I could call this logged add. right? Oops. Actually, I won't call it logged at. That's kind of stupid. So I'll change this very minimally from what I had before. There we go. Okay. So here, not anything too fancy. I just create a brand new function in here. All this function does is it computes the return value of the original function I passed in, logs everything to the console, and returns this. And I just return this logged function here. And instead of taking the arguments up here, this just takes the original function. Okay? And then I do this. What did I do? I wrote my function normally. Then I said, take that function, pass it into this log function, which dynamically creates a brand new function that calls the original thing I passed in, logs everything to the, so irritating. Logs everything to the screen, returns the original value. Remember that if I rewind a little bit, my original log function just had those same lines in slightly different order. This is what the original log function looked like. My new function just passes this in. That's what it looks like now. Slightly different. And then down here, I just say add equals log add. And you can see I have my little logging behavior here and here. Another common thing you might see about Python is Python programmers want to make your life easy. And so when they start to see very common patterns arise, they're usually pretty amenable to giving you simple syntax to make this easy. So a decorator, all a decorator is whenever you see the pattern of x equals some function called on x, where this x here is either a class or a def statement, you just replace it with this. This here is merely syntax for writing this at the end. That's it. There's nothing more to decorators. People like to talk about decorators as being a function that takes a function, returns a function. Really, all a decorator is an at that precedes a def that just means this. Add equals log add. That's all there is. Now, as a metaphor, the decorator itself does not introduce any new metaphors to Python. It doesn't. It's merely convenient syntax to access existing metaphors, where that existing metaphor is the idea that everything's an object, including functions. Everything is executed in this linear fashion. Therefore, you can create a function within a function, return it, reassign the name, and go along with your day, such that this end user code does not have to change. That's all there is to that feature. It's very simple. Let's look at a slightly harder feature. Generators. Now, a lot of you have used generators, but I find that a lot of people don't quite realize exactly what a generator is all about. I told you at the very beginning in the warm-up that there is a close correspondence between syntax like this and some underscore method. So I'm curious if you could tell me, what's the difference between this What's the difference between add 1 and add 2? If you're the user and you're not going to poke around in the internals. So obviously, you poke around in the internals, you can see. And don't say, well, they're written differently. Obviously, if you look at the source code, they're written differently. But from the perspective of a user, I told you that when you do something here with parentheses after it, it just calls this special method here. While you think about that, let me get this on the screen for you. And let me just pull this up in a Python terminal. Add 1, 10, and 20. What's 10 plus 20? Nobody knows. It's 30. Add 2, 100 plus 200. What's 100 plus 200? Type error. No, it's 300. It's 300. Well, I can't tell the difference between the two of these. Like from an end user perspective, what's the difference? I mean, they're both things that have parentheses after them that add. In fact, if you first wrote this and then you swapped it out with this, I'd never know the difference. Remember how I told you there's a really easy way to write things in Python that doesn't solve every problem, and then a slightly harder way to write it that solves a couple more problems? This might be an example of just that. In fact, let me make this a little bit fancier. I'll show you one way where you can immediately see a difference. Are these different? Yeah, every time I call add2, this secret little number behind the scenes gets stuck into the result. Let's rerun that again. Oh, this should be self.i. That guy gets added in there. Something interesting is happening here. There's actually a way you can do it in add1 using a closure. We won't talk about that. We do not have enough time to talk about closure object equivalence. But the idea being here that maybe if you needed to have some local state for this function, this might be an easy way to write it. You need to have some little counter that kind of takes a function that looks like it doesn't take any arguments and slip in an extra argument in there that you can manipulate. Let me start over. I told you that everything in Python, I didn't say everything because that's too much, but I told you a lot of things in Python. There's some syntax and there's some corresponding underscore methods. Well, if I say this, if I have some code that looks like this, x for x and xs, do something with x, what actually happens behind the scenes? I'll tell you behind the scenes, internally, if you look at the bytecode, Python does the following. So not literally, but in a, say, figurative way, Python takes simple code for x and xs and turns it into some structure that looks like this. I say not literally because it doesn't actually literally go in there and perform this translation. But what I'm trying to express is that if you look at what actually happens when you call this, this is what happens behind the scenes. Code that looks like this. Well, look, there's a top-level function here and a top-level function here. Okay? There's two top-level functions. You think you can override what they do? Of course you can. What are the names of the functions that you implement to override them? Well, just the word iter with underscores before and the word next with underscores before. So let's think about that. That means, and I don't know all the arguments that get passed. Well, actually, these don't take any arguments. I don't know all the arguments get passed to all the functions. Actually, we'll call this simple foo. And we'll initialize this. Okay? I know I can fit this into my iteration syntax because I know behind the scenes, in order to be able to iterate over something, I just have to be able to call itera next. Right? This is going somewhere, don't worry. This is going somewhere. So I could say for x in foo, print x, and you'll see it starts printing numbers to the screen. It just calls iter, which doesn't do anything interesting at all, and it calls next, which just does this. Let's think about this for a second. This is kind of interesting, right? Because notice, what could go under this next function could be anything. Here, we kind of think about this for loop as, oh, you're iterating over the elements in something, but anything could go under this next clause, right? Anything that I could put into a normal function, an unbounded amount of stuff. What if I had some really slow computation that I put here? And we'll just represent, instead of writing out a slow computation, I'll just represent it by a sleep. It's my representation for a slow computation. You notice every time you iterate over this foo object, it's able to perform any arbitrary computation, including a slow one, but it only performs the computation when you ask for the next element. For example, let's save this. If I say for index x in enumerate foo, if index greater than 5, break out of the loop. Otherwise, print x. What'll it do? It'll go through my little object. It'll try and grab the first 5 elements. As part of grabbing each subsequent element, it'll perform my slow computation, i.e. my sleep. And you can see that's one slow computation, 2, 3, 4, 5. But if you think about it, you needed to get 6 index. Remember, the enumerate starts counting from 0, so that's why we had 6 things showing here. But if you think about it, this could be any very long computation that can maintain some state because it's attached to some object. So like in the previous example where I added in self.I, it was some state that would get incremented and mutate or affect the computation every time. I could have that under this next. And I'm only paying for the computation as I do the iterations. Let's start over. See if we can kind of mix these things together. So what I said was I can have some class, and that class can have some internal state, something that it keeps track of, right? I can put a call method on it, and I can make use of that state, right? Here I'm making use of that state. Instead of putting a call method on it, I could put an iter method on it, and a next method, and do exactly what I was going to do in that call method, except I can't take arguments, but I could still make use of that state. And the only difference between this next method and the call method is the call method I could pass arguments, the next method I can't pass arguments. There's no way in the syntax to put that in there. Not quite. We won't get into how you actually do that, but not quite. And this is more or less equivalent to my kind of function written using call. That's all a generator is. When I write some generator like this, this is just some really simple syntax to write something that looks like this. And let me and in fact, if you really squint, can't you see all the common pieces? I started this off by saying, if you want to write a function, you could write it in both fashions. You see how there's a correspondence between these? These are both essentially simple syntax to implement this generator formulation and this function formulation, just very simple syntax to fit into the Python protocols. That's all a generator really is. People talk about generators. They're merely some syntax to fit into this structure. However, unlike the decorator, where the decorator was purely syntax, the generator brings with it certain metaphorical implications. And the metaphorical implications are as follows. Let's think about this for a second. This call function may perform a slow computation, right? But every time I call this call function, it only has the ability to, this call function may perform some slow computation. Say it's returning multiple values. And every time I call this call function, I'm essentially restarting that computation. Notice here, I restart the computation from the top every time. In this generator, notice I don't restart the computation. Every time I yield control back to the user, and the computation doesn't get restarted. The generator has a couple of implications. One of them is, ignoring that behind the scenes, it's just some object protocols that are set up. Behind the scenes, if this generator wanted to return multiple values, like a list of values, and this function wanted to return a list of values, and they both did this by making use of some very slow computational function, the functional formulation would be eager, and the generator function would be lazy. Let me show you this with a common example with generators. One of the most common examples that people use for generators is a generator that gives you values off of the Fibonacci sequence. And the reason they do that is because its implementation is fairly easy to read. Looks like this. And when you look at this in correspondence to the functional implementation, you begin to see some of the metaphorical implications here. And then we use this same line here. Let's squint and take a look at the differences here. Well, notice the Fibonacci in the functional formulation had to allocate storage for where the return value was going. Generator didn't allocate any storage. Why? Because the syntax for the two is slightly different. Next, let's look at this. Notice that the Fibonacci sequence had to tell you how many values you were pulling out. Here it's pulling out 10 values. Whereas the generator formulation just runs forever. Why? Think about the syntax. The syntax for calling says, go off, do this computation, give me the result. It's eager. When we call this, we have some result equals fib, like that. And it goes off, it calls this function, takes all the cost of going through this loop 10 times. Maybe I'll simulate some hard function. It pays for all that cost up front and gives you the result. In the generator formulation, if I mock up some long-running or complex computation in there, notice we don't pay the cost up front, because by virtue of the syntax, each time we ask for another item out of this stream, we then pay that cost. And so, if we do not ask for many items out of the stream, if we, for example, only ask for the first 5, we only pay the cost for the first 5 computations. You'll see with these two very simple formulations of essentially the same thing, that first metaphorical implementation. Generators are lazy constructs. Generators do not provide or do not perform computations until you ask them to. Whereas functions necessarily have one entrance and one exit, and between that entrance up here and the exit, wherever that return is, they have to pay the cost of every computation they do because they have no chance to defer that computation anywhere else. Whereas the generator does not have to pay that cost. You have one entrance point, and then you yield a value, but you don't close the generator. You don't stop. You don't destroy the state that's there. You keep that state around, and if you want the next value, you just resume from where you left off. That's one of the fundamental metaphorical implications of a generator. There's more to a generator that is very important. And this is something that most people do not see about generators. Generators are not fundamentally just about laziness versus eagerness. There's one other piece. You've all seen code that looks like this. Right? And I'll actually make this a little bit so you'll see this. You've all seen some class where somewhere in the documentation somebody said, here's 3 methods on this class. Call them in this order or else. If you call this last one here first, things blow up. Maybe this one sets up a database connection, this one closes the database connection, and this one here does something with the database. So if you try and close the connection before you opened it, all hell breaks loose. In user code, somebody probably then did this. Because even though the names are very clear, this class is fundamentally lying to you. The structure of the class says you could call these in any order. The names tell you something different. But I'm sure we've all had a situation where, what was said was not what was meant. Where do generators come into this? Think about this. Here, we have a computation that's split into 3 parts that can be run in any order whatsoever. Here we have a generator that has 3 computations. And remember, a generator only ever performs a computation when you ask it to. So the way you'd use this is you'd say something like this. That's the first computation, the second computation, the last computation, right? Can you call these in the wrong order in the generator? No. So fundamental things about generators is that they enforce sequencing. Generators are not just laziness versus eagerness, but they are about the enforcement of sequencing because they allow you to break up a single computation into specific parts. Normally that computation is done in sequence because that computation is building some structure like the elements from, or performing some operation in a natural order, like what's the next element out of this Fibonacci sequence. But there's no reason why the generator can't be just performing arbitrary functions in unenforced sequencing. That brings us to the last topic I want to talk about. And hopefully we'll get through this. Context managers. There is a very simple metaphor for context managers. For generators, I know a lot of you may have missed why that last metaphor was important. In this example, you'll see all of this come together, and you'll see why these metaphors, understanding these metaphors, even if you never remember the syntax until you need it, is so important. Many of you have seen the context manager structure like this. Let's do this. Let's make this ctx.py. Yeah, go ahead.
Can you please change the layers of the colors? It's a gray on gray. Hard to see.
Well, now it's a little bit late. How about this? That better?
Yes.
Yes, no? You want another joke? I'll tell you another joke if that helps you. Here we go. We've all seen context managers before. You have them, you have something that looks like this. With, open, some file name. Let's even open ourselves. tx.py as f, for line and f, print out the lines, right? And the reason that we were told context managers are important is because in a simple structure like this, we ensure that if you leave this block, the file gets closed. Many of us have seen the context manager in the context of things like database connections. So you can say with connect, test.db as connection, cursor equals connection.cursor, cur.execute, and then some SQL here. You've seen people write this. The reason people write this is they want to say, if you open the database, you want to close the database. The metaphor should jump out at you. Context managers are all about how do we perform some action such that there's some corresponding setup and teardown. And if we do the setup, we're sure to do the teardown. And search through all of the problems that you've worked on where if you set it up, you got to tear it down. If you start it, you got to clean up. A lot of different things look like that, right? I want to show you an example using this SQLite example that brings together all of the metaphors. One of the things that we might do in an SQLite database like this is create a temporary table. What do you think we probably want to do after we're done using that temporary table? We want to drop it. Well, look, there's a corresponding setup and teardown. The setup is create the temporary table. The teardown is destroy the temporary table. We want to make sure the teardown always occurs if the setup occurred. And we want to make sure there's no way for us to easily avoid that happening. What we also know is that in Python, for every piece of syntax, like with x as, or with ctx as x, there's probably some corresponding underscore methods. I'll tell you what happens here. This more or less turns into the following. Enter, try, whatever was there, finally, x.exit. There's no top-level function for these. You can see quite clearly what you need to implement in order to build your own context manager. Some function called enter and some function called exit. I warn you, I never remember what the arguments for enter and exit are. I always have to look at the documentation. I know a lot about context managers, but knowing the arguments themselves just simply doesn't matter. Doesn't matter that much. Knowing what it's for matters far more. And what it's for is, I do some setup, and I want to do some teardown, and I need to keep those closely linked, and I need to make sure I don't accidentally forget the teardown. Let me show you how to implement a context manager that would create a temporary table in a database. So maybe we create a temporary table with this cursor, and we'll just hard code what that temporary table looks like. And we'll say for row in cur.select, select star from temp. We'll just print out the results of this, okay? Well, I know it needs to have some class, and the class will be called temp table. I know it needs to take some cursor, because I'll need to use that cursor to actually execute stuff against the database, so I'll just save that. I know it needs to implement enter, and it needs to implement exit. I do not ever remember what the arguments for exit is, and you'll see why I don't, but I don't. Turns out I don't have to because they're not that important. What do I do on enter? On enter, I might just do cur.execute, create table temp, and then definition. Maybe we have x as an int and y as an int. That's right, I think. And then on exit, we might just do cur.execute, drop table temp. Okay? Pretty simple. Let's see if this actually worked. I'm not convinced I got that one right. Oh yes, thank you. Someone's paying attention. Because I stopped telling jokes, that's why. And you can see our color changing has never works out perfectly. Oh, this should be cur.execute. Oh, there we go. And we need to insert. Let's do a little bit of insert. So we did this. We'll say cur.execute, insert into temp xy values 1, 1. Actually, we'll do this. Da-da-da, da-da-da. And we'll say for xy in zip range 10 to 20. There we go. So we'll insert a couple of values and we'll just select them out, okay? There we go. You saw the values got inserted, selected, and you see every time I run this, if there's a little error in this statement here, by virtue of using the context manager, when I run this again, temp table already exists, so we got to do, the exit didn't get called. Let's do, the exit kind of failed to get called correctly. But ideally, the exit gets called and the thing gets cleaned up after itself. That's the idea. Sometimes it works, sometimes it doesn't. I want to show you something kind of interesting. You see the enter and exit have a sequencing to them? The enter always comes before the exit. What structure in Python is good for enforcing sequencing? That implies a core metaphor of sequencing. Generators. That's kind of interesting, right? So maybe I could take this and this statement and stick them into a generator. And maybe the generator would take the cursor as its argument and call this one and put a yield in between, right? Enforcing sequencing. And now my temp table is now kind of fancy because what it'll do is it might say self.g equals an instance of this generator, and it might just do next of my generator here and then next there. And I might do, actually, this is a little bit, you got to do it like this. Of course, the details are always a little trickier, but self.g equals g tt of cur. There. And then I actually have to do this. These are all details that simply do not matter. Okay, there we go. And you can see this thing works. And all I've done is now this thing just takes some generator and it puts it into the context manager protocol. And my generator here just enforces the sequencing of creating the table and tearing down. Well, let me call this something better. Like that. And I won't take this argument here. I'll just move that into here. And I'll leave the rest the same. So the init doesn't need to take anything. Actually, I'll take the generator as my argument. And I'll just do this. I'll call this GI for generator instance. There. Haven't done anything too magical. Now this thing doesn't really reference that it's ever a temp table. I'll call this thing up here temp table. And you can see it enforces the sequencing. And then I'll just do this. Temp table equals context manager temp table. To turn my generator into something that fits into this protocol, right? I just pass this in here as this argument, right? I capture the generator that was passed in. On enter, I capture the cursor. I advance through the first argument here. On exit, I advance the next argument, and I'm done. And we gotta make sure we spelled these things right. Context manager. And then this, oh, and we gotta do, oh yeah, there's a little trickier than that, but you'll see. Just do this. Let's stick it here. A little trickier. There's always a couple more details than you think. But the details simply don't matter. What matters here, what fundamentally matters here, it's always more details than you think, but what simply matters here is that what we have here is this context manager thing, this generator that enforces the sequencing, and this line here that turns our generator into a context manager, right? Now let me fix the bug that I had in it originally, and the bug is that this needs to take a cursor here, because I want to show you something kind of interesting. Notice that this thing now has a call method because it's called. So we'll bind the cursor in this call method here. That's what we're missing. And then this will work. And we'll turn self. Okay, so now this still works. Notice something really interesting here. I'm just going to move this code down to the bottom. Do you see a pattern here? Ever seen this pattern before? Something equals call a function on something, and that original thing was a function. You ever seen that pattern before? What was it called? It's a decorator. Oh, our code still works. And it turns out my sloppy, crappy version of this that I wrote, we don't have to write, it already exists in context lib. Here we go. Here we have an example of a context manager, a generator, and a decorator all together in one place. What you can see is each of these features has a fundamental metaphor behind it. One of the fundamental metaphors of generators is enforcing sequencing, which is important because we have to do the create the table before we drop the table. We fit this into a context manager. The fundamental metaphor of context managers is some teardown, some setup, and some teardown that are paired together. We have that here as well. We gotta create the temp table, and if we create it, we gotta make sure we destroy it. The last piece is a little bit of syntax because we wanna fit this structure into the protocol, a Python protocol of enter and exit. And the way that we do that is by calling a function that takes a function or a generator, and we have our decorator syntax here. Do you see how it didn't really matter? In order to get the code to actually work, we had to futz around a little bit. We had to move lines around. It got a little bit confusing. Probably would have helped if we had read through the documentation beforehand. Probably would have helped if maybe I warmed you up with a few more jokes. I don't know. But it doesn't matter. It fundamentally doesn't matter. When you need to know the syntax, you'll go look it up. What you might never be able to find from the documentation is, what do these features actually mean? What are they actually for? Who cares? Why do people care about them? And I think you see in the course of last 90 minutes, I showed you 4 core parts of Python, and I told you what each of them really fundamentally means. Let me review. Metaclasses. They might mean many different things, and they might be used or misused in many different places. But fundamentally, they are your core or primary way to make sure that if you have a class and someone's going to derive from that class, that they do something you want them to do, or don't do something you don't want them to do. How do you do that? Well, they give you an area where you can write arbitrary code to check their work. When they try to create their derived class, you have a little function that you can hook into, and you can say, hey, you didn't implement this method I wanted. This method I marked as abstract, you didn't implement it. This method that you wrote, I'm going to wrap it and change its behavior slightly. That's all it is. A meta class is just, in that split screen, we're not on the right-hand side anymore, we're on the left-hand side, and we need to make sure people who use our code on the right-hand side do things in a certain way by forcing ourselves onto them by means of this hook. It's all a meta class is. Decorator, merely syntax that makes it convenient to use a core aspect of Python, namely that everything is an object and everything is executed in this linear fashion from top to bottom, including things like class statements or function or generator definitions. Because they're dynamic, because they're executed at runtime, it means we can create classes within functions, create functions within functions. Because they're executed, it means we can pass a function to another function as an argument. And the decorator is merely a convenient syntax to take this common pattern we see in code, make it easier to use. The generator is merely a way to very easily write something that can be iterated over, where the key part is that on each iteration, what you do might be some interesting computation, as opposed to just looking at the next element of a list or the next element here. You can think fundamentally the easiest way to bridge the two is that usually when you think about iteration, you think about getting the next item from some sequence. What if that sequence is a row in a database? Getting the next item is a complex operation. It's a network call. You have to go out into the network, send some information to the database, wait for it to come back. A generator is not how those are typically implemented. They're typically implemented in terms of iter and next that we saw before. But you can think there's a similarity between what is done there and the core of what a generator provides you. But one side effect of that, or one consequence of that, is that generators also fundamentally enforce the sequencing of operations, because when you yield from a generator and you resume, you can only resume from the point where you last left off. Finally, a context manager has a simple metaphor, the simplest of all. Do something to set up some state or some context, and make sure you clean up after yourself afterwards. If you open the cupboard to get a cup, make sure you close it. I never do that. If you come to my house, now that we're all friends, if you ever come to my house and I make you a cup of tea, please remind me to close the cabinets, because I seriously leave them open all the time. And please also remind me to unplug the kettle, because it's really a fire hazard. I have it right next to my toaster. If only there were context managers for real life, but they're not. Well, I guess they are. That would be like a housekeeper or something. Okay, we're getting too far off track. Fundamentally, a context manager is this pairing of setup and teardown. And in the example I show you here, you can see all of them coming together. The syntax for them, of course, you saw, I struggled a little bit to get it right. I struggled to remember all of the arguments, but it doesn't matter. When you see each of these independently, you can now begin to think, well, I want my temporary table to be created before it's dropped. That sounds like sequencing. Makes sense for that to be a generator. If I'm going to write as a generator, I need to fit it into this protocol. So I need to have some class in the middle. In order to pass my generator into that class, I need some syntax that looks really similar to the decorator syntax. And there we go. All of the pieces fit together in one. And they fit together fairly seamlessly. I'll finish this example. There's one last thing I have to do to make this correct. And here, this should stand as a complete and correct example of how to create a context manager using a decorator and a generator. Unfortunately, I can't stick a meta class in here as well. Or I could, but it would be gratuitous. But you see there are some metaphors behind the scenes. Should you use these features all over the place? No, of course not. But now I hope that all of you will understand that the details of these features are important when you need to use them. And if you find that you need to use them, you'll have to look at the details and say, is this something I can really use or not? But I hope that all of you, especially those of you who aren't commonly using these parts of Python every day, at least have a starting point where you can say, hey, this problem looks like something I've seen before. It's probably a good use of a generator. This problem looks like something I've seen before. It's probably a good use of a meta class. And if you can understand that and really fundamentally intuit how Python was designed and what these features are really for. The rest is just details, which you'll look up when you need to. So those were the 4 things I wanted to go over. I'll open for questions. I don't know how much time we have left since our schedule is a little bit different, but any questions? We have 10 minutes. That's good. In the front first. What's your name? Stefan. How you doing, Stefan? Stefan has enough friends. He doesn't need another friend, apparently.
You can be my friend.
Oh, I can be Stefan's friend. Fantastic. Well,
you showed us how we can use meta classes to test if the deriving class has an attribute. And you also mentioned you used this to like in this example where you made sure that they did this database connection.
I just wrapped their function. So when I got their derived class, yeah, so the question is, I brought up an example where I used the meta class not to check something, but to enforce some behavior. The way it is in the meta class, I get the class you're trying to construct, right? I can look at it and make sure that it satisfies some requirements that I have, but I can also change it. And so I can just take any method you write, and I can wrap it using the same trick I did with the decorator with my own method that does the things I want. So that was my solution. My solution was, don't bother to even have them call the special database setup method. We'll just take their methods that they write and wrap them ourselves. And maybe behind the scenes check the environment to see if the task needs to be done or not. There was another question.
How can yield ever throw an exception?
What happens in this case, the question is how can yield ever throw an exception? What happens in this case is that when you need to be able to capture that exception if it occurs, because you might need to do something with it. So what happens here is that generators are a lot richer than just next. They have 2 other methods on them. One of them is called send, the other one's called throw. Send allows you to do something a little bit more sophisticated with generators and introduces a brand new metaphor. That brand new metaphor is what's called a coroutine. What we saw with a generator versus a function is that a function starts at one point, runs to the end. With a generator, it starts at one point, and then you can kind of enter and re-enter. How do you stick information back in every time you re-enter? That's a generalization from a subroutine that takes some arguments and runs to completion, and a coroutine that takes some arguments, runs to some point, pauses, allows you to pass in more arguments, pauses, allows you to pass in more arguments, pauses. By the way, coroutines are a very important part of asynchronous programming in Python. The best asynchronous libraries in Python, namely Curio and Trio, well, okay, the ones I like the most, maybe not the best, but the ones I like the most are built all around the idea of coroutines. Well, that's what send is for. What's throw for? Throw allows you to throw an exception back up into a generator. What happens in this context manager adapter is that when an exception occurs inside the context manager knows it because those are what the arguments to exit were. The ones I can't remember the name of, it's like exception value, exception type, things like that. It'll take that and it'll throw them back up into the yield, and the exception will be percolated on line 10 here. That's how a yield can actually raise an exception. It's not being raised by the statement itself, it's being re-injected into the generator from the outside. To really understand that, you'll have to look at how coroutines work, because I think they're very closely tied. Other questions? Anyone actually going to use any of these features when they get back to work? Who wasn't going to use them before? Nobody. So everyone's going to use them before, and they're going to keep using them. So I didn't scare you away from the features. That's good. You're just maybe more confident in using, I don't know. But you can see they mean something much deeper than just, oh, here's some syntax. The syntax is the least interesting part of them. There's a question. Oh, was there not a question?
No, I just didn't get your question.
Okay. Well, that's what I wanted to show you. This is something which I wanted to shortcut for you what I think takes a long time for people to build in their mind. People use these features for years and years and years, and they keep throwing mental models against the wall for how these things work and what they mean until one sticks. What I wanted to shortcut for you is you use these things enough and you start to see patterns. You try to figure out what do these patterns imply. You distill that, and there you have a 90-minute PyData talk. Anyone can do it. So there you go. I hope you enjoyed that. Thank you very much.